Hello everyone, this is our first section of the course starting in chapter 6. So section 6.1 deals with inverse functions. We're going to go through quite a few definitions and theorems, review what an inverse function is, some properties and characteristics of them, how to find them, and also how to find the derivative of an inverse function. Our first definition is a one-to-one function. So we'll say a function f is called one-to-one. And the notation for one-to-one, we'll just say 1-1 here, so that's one-to-one. If we have two different x values. So if our first x value is not equal to our second x value, and then this implies that our outputs are also different, so that our first y value, or f of x sub 1, will not equal our second y value, f of x sub 2. In other words, different inputs yield different outputs. Whenever I explain what a function is, remember how that has to pass a vertical line test? And for a relation to be a function, we want all x values to be different. So here we also want all x values to be different, but then we also want all y values to be different. In some of the ways we're going to check, we're going to use this. So we'll say, for example, if our outputs happen to be the same, so if f of x sub 1 does equal f of x sub 2, that can only happen if our two x values are equal. And this is kind of how we verify algebraically. So if f of x sub 1 is equal to f of x sub 2, then x sub 1 is equal to x sub 2. So in other words, if the outputs are the same, then the inputs must have been the same. So I would definitely copy that down. It's just a different way to describe this. If the outputs are the same, then the inputs must have been the same. All right, just as I mentioned, a function itself has to pass a vertical line test, but a one-to-one function needs to pass a horizontal line test. So we'll say a function f is one-to-one if and only if a function f is one-to-one, if and only if, looks like the if with the two f's here, if and only if a horizontal line intersects its graph no more than once. So graphically, this is how we could tell. So a function f is one-to-one if and only if a horizontal line intersects its graph no more than once. Okay, so we'll look at three examples really. So the first one, we're just going to sketch a graph for. Is f of x, which is equal to x squared, would that be one-to-one? So let's go ahead and make a sketch of this graph. We know y equals x squared is just going to be a parabola with a vertex at the origin. So we'll draw something like this. And the quickest way to decide this is by using the horizontal line test. So we could see we draw a series of horizontal lines, and we notice it definitely passes through the graph more than once. So we would say no. And to go back to the very beginning, what we're looking at here, if let's say we would have f of 1, that would equal 1. And then even f of negative 1 would equal 1. So our outputs are the same. And remember, that means if our outputs are the same, then the inputs must have been the same. But the inputs were 1 and negative 1. And they are definitely not equal. So no for two reasons. Graphically, we see that it does not pass the horizontal line test. And I'll abbreviate HLT, horizontal line test. Also, because we have two outputs that are the same, but the inputs aren't the same. So that's going back to what I have here in green. If the outputs are the same, then the inputs must have been the same, and they're definitely not. Another example is f of x, which is equal to x cubed, 1 to 1. You guys remember what the graph of y equals x cubed looks like? Hopefully you do. If not, you can always pick some values. So it starts over here, crosses at the origin, and then tends to go up. So would this pass the horizontal line test? Absolutely. So we would say yes. This passes the horizontal line test. So in other words, every output is going to be different. Let's take a look at this, just not graphically. So is f of x, which is equal to x cubed plus 4, 1 to 1? Well, f of x, which was equal to x cubed in our last example, was 1 to 1, and this is just shifting that 4 units up. So we would expect it to maintain the same behavior, so it should also be 1 to 1. But here's a way that we're going to show this. Right now, let's just suppose that the outputs are the same. If they are, then x sub 1, our first x value, our first input cubed, plus 4, should equal our second input cubed, plus 4. Now I'm going to just go ahead and subtract 4 from both sides, so our first x value cubed should equal our second x value cubed. And then I'm going to take the cubed root of both sides, and x sub 1 is equal to x sub 2. So because it worked out that way, if our outputs were the same, then our inputs must have been the same, and we just show that they are. So we would say, yes, it is 1 to 1. All right, let's take a look at some relationships between a function and its inverse. So here we're going to write out, we'll just say let f be a one-to-one function. With domain A and range B. Then its inverse function we'll use this notation. That's the notation we use for the inverse function. So the inverse function, yes, f to the negative first, but that's just the notation we're using, has domain B and range A, and is defined by this equation right here. If and only if f of x is equal to y for any y contained in B. And this little symbol right here means contained or is an element of. So to kind of explain this better, let's just say we have our function over here. Let's say that this is f of x. This would have a domain. We're just calling it A for right now. We have a range we're going to call B. So for any x value we put in, we're going to get an output of y. Now our inverse function, our domain, would equal the range over here. So that would be whatever B is being described as. The range would be A. And then if we were to substitute a value in here, we would simply switch around the y and the x. So I'm actually going to erase this part up here. We'll just say f and then the inverse of f. Don't want to get too confused with the x's and y's with what I have written down here. Now, algebraically, to show that we're looking at a function and its inverse, the following must hold true. So the composition functions. So if we were to take the inverse function and compose it into the function itself, everything should cancel and we should be left with x. The symbol for every or for all is like an upside down capital A. For all x values contained in set B. And then if we were to take our function, f of x, and drop it into the inverse, that will also equal all x. Again, for all x values contained in set A. The B over here is just indicating that all of these x values have to apply to and agree with the domain of B. And then right here for f of x, we're going with our domain of A. So algebraically, to find the inverse of a one-to-one function, three steps here. Instead of using the notation f of x, we write y is equal to f of x. And we'll go through an example here in a second. The next step is once we replace the f of x with y, we simply switch x and y. Step 3, we end up solving for y again to get y is equal to the inverse of f of x. All right, so let's take a look at an example. Now, sometimes as I go through this, I might have you pause the video for you to figure things out on your own, just like in class. Before I go over a problem in its entirety, I'll have you guys work on it in class. So if you'd like to, pause the video here, follow those steps, see if you remember how to algebraically find the inverse of a function. If not, just let the video play and follow along. All right, so step 1, notice how this says f of x is equal to x minus 2 over x plus 2. We're going to just rewrite this as y equals x minus 2 over x plus 2. That's step 1. Step 2 is to switch around the x's and y's. So now we're going to get x is equal to y minus 2 over y plus 2. Step 3, we now want to solve for y. Well, we have a couple of y's here. So I'm going to put all these binomials in parentheses. I want to go ahead and multiply both sides by y plus 2. So in doing that, I'll get x times the quantity y plus 2 is going to equal y minus 2. I really don't need the parentheses over here. What I want to do next, I want to be able to combine all my y terms on one side. So I need to distribute this x here. So we're going to get xy plus 2x is going to equal y minus 2. I want to get all the y's to one side, so I'm going to leave the xy term here, subtract y. Over here, I'm going to subtract 2x, so we'll get a negative 2 minus 2x. Now I want to factor the y out, so we'll get x minus 1, and then still negative 2 minus 2x here. Solve for y, so y is going to equal negative 2 minus 2x over x minus 1, which this is also the notation for the inverse of f of x. So what I had explained at the very beginning with the definition here is the domain of this function is going to equal the range of this function down here. And then vice versa, the range of this function would be the domain of this function. And if you were to compose one into the other, everything should cancel and you should be left with x. All right, so let's take a look at how we can determine if a function is an inverse of something else graphically. So we'll say the graph of the inverse of f is obtained by reflecting the graph of f about the line y equals x. All right, so you could just sketch this on notebook paper. If you do have graph paper and prefer to sketch this on there, you can. So again, the graph of an inverse of f is obtained by reflecting the graph of f about the line y equals x. I'm just going to plot some points here. I'm just going to go to 0, 1. And if I count it over 1, let's say I'm counting up 2. And if I count over 2, let's count up 8. So this is just like one side, one half of a parabola that I'm going to graph here. Now really, if we're just switching the x's and y's, if I have the point 0, 1 on my function, then the point 1, 0 is going to show up on the inverse. Here I have the point 1, 3, so I'm going to have 3, 1. And up here I have the point 2, 9, so I'm going to go to 9, 2. I'm actually going to color code these here. So I have 0, 1, I've got 1, 3, and 2, 9. This is all on the graph of f. Over here I have 1, 0, I have 3, 1, and then I have 9, 2. This is on the graph of the inverse. If I were to draw the line y equals x, I would go right up through the middle here. And you could see that it would be a reflection. The inverse would be a reflection over this line. And that's what this definition or description is taking a look at. So one thing to point out, what I'm going to write here, is if 0, 1 is contained or is an element of f of x, then 1, 0 would be contained on the inverse. So I'm not going to refer back to this graph. Let's just try an extra example that I want you guys to fill in the blanks. So let's say if the inverse of f of 3 is equal to 6, then f of 6 is going to equal what? So in other words, what this part is saying right here, this is the input, this is the output on our inverse function. So we would say 3, 6 is contained on the inverse of the function. Over here then, f of 6 should equal 3, because this means then 6, 3 is contained on the function itself. So we're just switching them around. So let's try one more. If the inverse of f of negative 2 is equal to 0, then f of 0 is equal to what? If you're thinking negative 2, you would be correct. Because again, what this means is the point negative 2, 0 is contained on the inverse, then 0, negative 2 is contained on our function. This brings us to a short little theorem here. If f is a one-to-one continuous function defined on an interval, then its inverse is also. So if f is a one-to-one continuous function defined on an interval, then its inverse function is also continuous. All right, our next theorem, we are now going to take a look at how to find the derivative of an inverse function. So we'll call this inverse differentiable. I'll just abbreviate that here. And this says if f is a one-to-one differentiable function, with inverse function, we'll call it g, which would equal the inverse of f, and as long as the derivative of f of g of a is not equal to 0, and you'll see why here in a little bit, then the inverse function is differentiable at a, and the formula for the derivative of the inverse, so remember I'm calling g the inverse, so we would say g prime at a is equal to 1 over f prime of g of a. And it's just a lot easier to say g than the inverse. So f prime of g of a, and because it's in our denominator now, that's why it can't equal 0. So going back to another way to write this, instead of g, we would say, but you could see how much more complicated this looks using the actual inverse notation. But this would be the derivative of the inverse at a would be the same as 1 over f prime of the inverse evaluated at x equals a. But both of these are decent formulas that we can keep using for our examples. Okay, so this last example, we're going to figure this out two different ways. So we're going to let f of x equal the square root of x minus 2. We are going to find the derivative of the inverse at x equals 2 using the new theorem I just wrote out. And then for b, we're going to find the derivative of the inverse by finding the formula for the inverse first. So let's go to part A. So we know that f, and again, let's just go back. This is the formula I'm going to use here. So we know that the inverse, the derivative of the inverse at x equals 2 is going to become 1 over f prime, the inverse of f of 2. Well, we need to figure this part out first. So we're going to go off to the side here. We need to figure out what the inverse of f of 2 is going to equal. I'm going to call that u for right now. So if you remember, this means that the ordered pair 2 comma u is contained on the inverse. What that also helps us to understand is that u comma 2 would be contained on f. And we could figure u out now, because if I go back up here, there's my function f of x. So that means f of x is equal to 2. So I'm going to set 2 equal to the square root of u minus 2. I'm going to square both sides, so we're going to get 4 is equal to u minus 2. And then u is equal to 6. So therefore, we're going to say that the inverse of f of 2 is equal to 6. So now I can continue over here. I'm one step closer. Now this becomes 1 over f prime of 6. So my next step, I need to figure out what f prime of x is. So I'm going to continue that over here. So now f prime of x, I need to take the derivative of this right here. So if you remember, we can also write this as x minus 2 to the 1/2. We're going to use the chain rule to find the derivative. So I'll just fill this in up here so we could still see it. Right, so the derivative now becomes, bring down that 1/2. Stuff inside stays the same. Then I subtract 1 from the exponent, so to the negative 1/2. Then it's really times the derivative of what's inside. The derivative of what's inside is really a 1, so I don't have to write times 1. It's not going to change anything. So then this becomes 1 over, I'm going to keep that 2 down here, and then this goes back to the square root of x minus 2. So that's my derivative. Now let's figure this out, what f prime of 6 is. So I do all my work off to the side, and then I could slowly fill in my steps. So f prime of 6 becomes 1 over 2 times the square root of 6 minus 2. We get 1 over 2 times the square root of 4. That's 2 times 2, so we get 1/4. So my final answer is, 1 over 1/4. And that's like multiplying top and bottom by 4, so it's really the reciprocal, so we get 4. Right, so that's following the rule for the derivative of an inverse. Now let's try this part B. Let's find the function for the formula or expression for the inverse of f. So let's go back to if f of x is equal to the square root of x minus 2. Let's go through those 3 steps for algebraically finding the inverse of a function. So first we say y is going to equal the square root of x minus 2. Switch x and y, so x is going to equal the square root of y minus 2. We're going to square both sides, so x squared is going to equal y minus 2. Because we want to solve for y. And then my last step is just to add 2. I'm going to switch this around, so y is going to equal x squared plus 2. Therefore, my inverse of f of x is equal to x squared plus 2. Now all I have to do, this might be a little bit easier this way, all I have to do now is find the derivative of this expression right here, but I'm going to write it this way. Here's how I write the derivative of the inverse. This just becomes a 2x. Now if I evaluate this at x equals 2, because that's what we wanted to find, this becomes 2 times 2, which is also 4. So let's go ahead and check this graphically. If you have a graphing calculator, please get that out. If not, you can go to Desmos.com. It's a wonderful website that allows you to treat it as a graphing calculator. There's so much more you could do with it as well. But if you go to Desmos.com or on your graphing calculator, let's go ahead and just type in our function, which is the square root of x minus 2. So that's what our function looks like. Then all you have to do, if you're not familiar with Desmos, just hit right below it to start a new line. And then we want to type in our function, which is x squared plus 2. But this is going to look a little different, only because we only have the upper half of the square root. So we're going to see an entire parabola, but just know we're looking at just the right half of it. So we're going to have x squared plus 2. But the part we're focusing on is just from the y-axis over. If we were to draw the line in of y equals x, there's what it would reflect over, but again, we're just looking at right here. Then I'm also going to plot the point. We'll go 2, 4. I'm sorry, 2, 6 is what it's going to be. All right, so it's at this point, we're on our inverse function right here. If I were to draw on a tangent line, it should have a slope of 4, and that's what we were doing when we were finding the derivative of the inverse at x equals 2. We're finding the derivative is the same as the slope of the tangent line. If you can imagine drawing a line in right there, that would be our derivative. All right, so this was our first section here, going over inverse functions and the derivative of an inverse function. So all of these examples should be plenty to help you with the WebAssign assignment, but let me know if you guys have any questions.